So shall we start, Luciano?
Yes.
So our first speaker from the program is Luciano Abriata, and he's going to talk about what I call MoleculARweb. So for me, it's a mystery. So I hope he is going to clarify what is all about this program that he's going to explain to all of us.
Yeah. Okay, good. Thank you. Thank you for the, you hear me well, right? You hear me?
Yeah.
Okay, perfect. So thank you for the invitation to talk, to present this work that we are doing. So I work at EPFL, which is the ETH, maybe more known, ETH, which is located in Zurich. EPFL means the same as ETH, but in French, because we are in the French-speaking part of Switzerland. It's located in Lausanne, that's why the L. And so I work in this institution where I work in two labs. In one lab, I do protein biophysics, essentially protein NMR, for several users. We have lots of projects. And then my other lab is this one, where I do molecular modeling and computer simulations, etc. And a couple of years ago, I started playing with some things that I will show you now that with time became very important, and we even got funding to present all this. So I will tell you what this is about. But so essentially what we are developing is a platform that works on the web, where you can use augmented reality to teach chemistry, or to help your teaching of chemistry and structural biology, using nothing more than normal smartphones and computers, okay? No fancy equipment. So the motivation for this is that, you know, I studied chemistry, and, you know, when you're studying chemistry, you have, I guess there are many chemists in the audience here, you have all these abstract concepts like reactivity, orbitals, molecular shapes. Then you get to know that the molecules are not static, but they actually move, and this gives you conformations, and then conformations exchange in equilibria. Then you have all the acids and bases, the hydrogen bonding that also gives you equilibria, dynamics related to how molecules move. Then molecules can also interact. There are many concepts that are a bit abstract, or maybe you can imagine them, but they actually happen in 3D. And most of the material that you have to when you are learning chemistry, or also when you are teaching chemistry, is intrinsically two-dimensional. It's just maybe a figure in a textbook, or even computer graphics on a flat screen. Okay, maybe some of you, at least I was lucky to have one of these kits when I was studying organic chemistry, where, you know, you can build all these plastic models of molecules, and then with them you can inspect molecules that are maybe complicated to imagine in 3D. You can even do some dynamics. For example, this is cyclohexane. You know, you can exchange between the boat and chair conformations, and this is something relevant, very important to study already, to learn already at the early stages, because then you see these everywhere, especially if you work with proteins, which have lots of degrees of motion. Then even for proteins, there are some plastic kits where you can build the backbone, and you can place some side chains. You see these kits here. Now these things, they have a couple of problems. First, that they are costly. Okay, you can build a cheap alternative by putting together balls of styrofoam connected with sticks or something like that. I had some friends at the university that were doing this, but many people are not motivated enough to do that. Okay, and if they cannot buy, then they don't have this resource. And then even if you have this, you are limited in the number of atoms that you have. Maybe this kit has, I don't know what, maybe 50 atoms, and there are only maybe 5-6 types of atoms. Typically, you have carbon, hydrogen, oxygen, nitrogen, some halogens, and that's it. Okay, so it's quite limited. You have to build the molecules, which is per se pedagogically something good, because you get to learn how the molecule is constituted. But when the molecule is too large or too complex, that gets complicated. There's not much dynamics other than some torsional angles or things like this that you can test. And then the kits are very limited. For example, with this, you can build only small molecules, and you can only see them at atomic level. With this, you can only build proteins, and you can only see them at the backbone level with some side chains. But it's quite limited, let's say. Then on the other hand, so this is very physical, but on the other hand, you have computer graphics. With computer graphics, you are essentially unlimited in the kind of information that you can display in 2D. You can see proteins, for example, like cartoons, and then you can give more detail to the side chains to try to understand the chemistry that is happening here. Same to see, say, protein DNA interactions. You can even map here this is X-ray diffraction data. You can even map it on top of the actual structure. This helps you to inspect the structure if you're doing research, or also if you're learning. This helps you to understand how experimental structures are determined. So graphics are very powerful, much more powerful than the plastic models. But this comes at the expense of control. When you have the molecule in your hands, you can do whatever you want to the atoms. You can move all angles very easily. It's very, very interactive. You can use the two hands to express what you are thinking directly on motions in 3D. But instead with the graphics, this is not so easy, because you are limited to one control, which is one mouse, and so you can move and drag molecules one at a time. So suppose that you want to do something that in structural biology, in research, we do this a lot, which is to inspect two molecules and try to see how they dock. Here you have to grab one, move it, then release it, go with the mouse to the other one, move it, release it. Instead, it would be much cooler if we could grab the two molecules and then put them in front of each other and move them independently at the same time. Well, in the near future, we will have this, because there are all these very advanced tools for molecular graphics and modeling that now are trying to blend the best from the physical and the virtual worlds. Okay, so like trying to have physical objects that allow you to grasp them, and then see virtual molecules that have a lot of information that can be augmented with even more information that the computer can calculate for you. And indeed, if you look at the recent literature, you have, for example, this maybe some of you know Chimera. It's a program for molecular modeling and visualization in the computer. Now it has a specialized version. It's called Chimera X, that is adapted to this kind of virtual reality devices, where you can grab a molecule and move it and zoom it, compare different molecules in a virtual reality environment using your hands, actually the controller, not the hands. And then you have even more advanced things like this, which is the core is similar to this, but it's coupled to molecular mechanics calculations in a way that you can not only move the object, but actually say open, for example. You can, for example, unfold the protein, okay? Or you can thread one molecule through another one. And this you see it in virtual reality. Moreover, in this work, what they did is that they coupled two persons who are independently working on the same physical system. So you can imagine these kind of things have lots of applications, of course, in research. They are not still at the level that you can already use today, but they are approaching at least a level that you can use them for education, okay? I recommend you also this very inspiring piece of literature that you can read. It has to do with this, but and also with other things. I don't want to spend time on it, but I wanted to highlight that, of course, all these kind of technologies where you have simulations and graphics are very enticing from a pedagogical point of view. They have a lot of pedagogical power, okay? And even more so if students and teachers can access this directly on the web without installing anything. In these cases, you have to have the hardware, which is expensive, and you also need to install some programs that may not be trivial for the average user. So here I'm skipping a few slides. I will show you just this. So what you are seeing here is called virtual reality. Virtual reality is something like this. So where you have this helmet and some controllers that you can use to handle the virtual objects. But the main thing is that you are entirely embedded in a virtual world. Okay, actually here we see what this person is seeing, and you see it's a fully virtual world, which has some applications. But then there's this other thing that is called augmented reality, where you have some kind of glasses that show you the real world, and on top of the real world it puts molecules or whatever object you want to study. Okay, so augmented reality, at least in this way, is more complicated to achieve than virtual reality, but it has some advantages. First, since you see your real hands, you have much better limb coordination. Here, you don't see your real hands. You only see a representation of the controller. So it has some lines, something like this, like what you see here. This is one of the hands of the person. Then in VR, after some time, you start to get sick because you lose total track of the reality, and so it can be problematic. In augmented reality, this is much less, because even nothing, because you see the real world around you. Then here, for virtual reality, you need a lot of space, because the person doesn't see the real world, so it's moving around, and it may tumble upon things, it may even fall, or who knows. Instead, this is not a problem in augmented reality. Then here, in augmented reality, the user remains much more integrated than in virtual reality, because in augmented reality, he's still seeing all the other people around. This is especially important if you imagine a student wearing these things. And then the most interesting thing for me is that this for sure requires these special devices. Augmented reality, you can also do it with special devices, but you can also do it in a simpler way, but still quite nice, I think, using commodity, what's called commodity, so cheap, inexpensive augmented reality. Similar to what you probably knew with Pokemon Go, okay? So through the phone, you hold your phone here, you see the real world, and on top of the real world, you see, all, in this case, all the Pokemon things lying around, and then you go and look for them. So this here is much more immersive than this kind of augmented reality, but this is prohibitively expensive. Actually, today, one of these sets can easily cost 2,000–3,000 francs, dollars. Instead, with this, you have a normal phone, a normal computer, and you just do it, use it. So following this idea, and especially the augmented reality technologies that work on the web, so you don't need to install anything, we started working on this that we call MoleculARweb, this website for chemistry and structural biology education, through augmented reality with interactive activities that you can use out of the box. It means that just enter the website and it will work, and for free, of course. I will go very briefly, but you have all the activities that I will show here, many more also, described in this preprint. So this is work, as I told you, this started as a hobby 2 years ago, 3 years ago, but then we got money from the Swiss Research Council to actually develop this into an actual product that people can use. And for this, it was critical to have a web AR, web VR engineer, it's Fabio Cortez, who developed everything I will show you from now, okay? We started working during the COVID pandemic. Fabio is from Colombia. I'm from Argentina, but living in Switzerland. Now he came here, but at that time he was working also from Colombia. And well, we were meeting every afternoon to discuss how things were going, next steps, etc. I would say that working online, at least with the computer, works very well. So essentially what you need is you have to access this website. Then you need to print some of these that are called augmented reality markers. This one is the one that you have here, and then you have these two. Different activities use different things. You can access this with a computer, with a lab, or with a phone, or with a tablet, etc. And then you have to choose. These are different modules where we incorporated activities related to different topics in chemistry and biochemistry. You have to choose a module and then an activity. So essentially what you do is you print the marker that you need for the activity, you fold it. For example, if it's a cube, you have to fold it like this, or this. Actually have two sides that you have to glue side by side, and you get this. You access the website with the device you want to use. And then you can manipulate the molecule or the orbital, whatever you want to study, to teach to your students, etc., directly with the markers. And you can see it in 3D there. Then this was the original thing, but recently we incorporated a way to see objects without any need for markers. We call this markerless augmented reality. We developed it at the moment only for chemical, so for biological assemblies, because they are big and they are nice to see. But essentially this detects a surface and then places the molecule there. And once the molecule is there, it stays. So you can move around, you can go inside. You see how here I'm walking around the DNA, and then I'm looking inside at the base stacking and pairing. And it's quite, I think it's quite nice. Well, I had many more slides, but I prefer to do a presentation live. So I will go here. I think you should be seeing my screen in Google Chrome. Yes, you see it. So here you have to choose an example. You just come here, then I have a list of things to show you. Atomic orbitals. So for example, let's go to this activity about atomic orbitals. When you get this, you say, okay, continue. And then here I have a problem with the camera. I will have to switch off the camera for a second while I'm talking. Just give me a second. It should be here. I will stop sharing webcam. Now I will go back. You will see me here anyway. I refresh, Continue. Okay, you should see me here. The video will be a bit slow because my computer is running lots of things, but I hope you see that I have these two markers. And in this case, what I'm displaying is, I need to see my second screen. I'm displaying the two s orbitals, but I can go, for example, and look for here, I don't know, maybe a 4f orbital, which is quite nice to see. Okay, so I have this one here. And since I have two independent markers, I can maybe choose two orbitals. Let's take this one and compare them. Okay, and you can rotate this. And once you see the other side of the marker, you see the other side of the atomic orbital. This you can also run it on the phone, and it will be the same. There are several controls here. In the paper, we will explain what they do, but essentially you can swap the camera. For example, if you're working on the phone, you have two cameras, so you can swap the camera. Then you can also swap video, which might be useful if you're studying chirality, to show how when you see the specular image, then the chirality changes, etc. Then the next example I put in a list to show you is this one about molecular shapes. Continue. And here in particular, maybe it would be good to show you this one and this one. These are two molecules of type MX5. Okay. However, they have different shapes. So again, since you have two markers, you can easily show how this one that I have on this hand, the one I'm moving now here, it's like a pyramid with a rectangular base. Instead, this one corresponds more, you see, to a bipyramid with a triangular base. And yeah, you have all the other examples that you can inspect there. I'm going very quickly, but another activity I will not show you, but you can go and play, is this one with many molecular orbitals for many molecules. Then the next example I have here to show you, yes, some of these activities are somewhat interactive. For example, here you have two water molecules. Okay, so each molecule, I will leave this, and I will use my finger to point at this here. You have the oxygen atom in red, and then the two hydrogens, and we also display the lone pairs that you have on the oxygen atom. And why do we display this? Because we want to illustrate what happens with hydrogen bonding. So, you know, when the two water molecules get close enough, you have a hydrogen bond that is shown in yellow, and then a proton transfer. And if you take them out quickly, you will get on this hand here a hydroxide, and then here a hydronium ion. Okay, and so this is the basis for the water, the weak but clear acidity and basicity that you have in water. This is the reason for the equilibrium of hydrogen exchange that you have in water. Another example I have, then you have also this for acids, etc. Another example I have in the list to show you, this is going more to protein structures. So this one, so continue. Here you can explain the two main secondary structures, so beta sheets, okay, and alpha helices, okay. So what we have here is that, of course, the protein is like any other, I don't know if it's this one, yes, like any other molecule, it's just atoms connected through bonds, so you see it like this, but there are some interactions that stabilize, especially all the network of hydrogen bonds connecting the backbone units between each amino acid and the one that follows 3, 4 residues later. Okay, so you get this. And to simplify the representation, what we actually do sometimes is to draw cartoons. Okay, and actually sometimes we even not draw the sticks at all. So this is the simplest representation. Then you have the same for the beta that you can load on the other marker. Going back, another example I have to show you is one a bit more complicated. So we have a list of biological assemblies that are all taken from actual experimental structures. Okay, so here you have this one or the other one. Yeah, here you have a ribosome, for example, that you can inspect. This is much better to inspect in another way that I will show you later. But essentially here you have the small subunit, the large subunit, then all the solid things are proteins, the sticks are RNA, and then if you zoom inside, it's hard to see in this way, but in the other application that doesn't use any model, you can see it better. You have here the interface, and if you zoom enough, you can see some other colors inside that correspond to the messenger RNA that is stuck there with some tRNAs. But there is another way to see it better. So then this other way to see it, I cannot show you, but because you need a phone. But I will show you this video. I will remove the audio. But essentially, so you go. If you open this with the phone, you can go to one activity. Like here, I loaded the same that I just showed you, RNA on a ribosome, okay? And then you click. I will click this. So here I am at the position, the place where I could use the marker. But instead of using the marker, I will click this, and then I load the model here. I can move it here, but the best is that I can click this. See in your space. We have all languages, including Portuguese, a very easy, probably with many errors, Portuguese, but you will find it. And then, so what you do with this is that you can locate the molecule somewhere there. Then you can watch the movie, the YouTube video if you want, or you can even try it. And then here, so you can move around the ribosome. And here, for example, I got inside the ribosome, and I'm showing you in red a tRNA, in magenta right there at the bottom. What you see, this magenta is a piece of messenger RNA, and the green is another tRNA that is base pairing. For example, here you see how this there are three. Each stick here is a base. How they are pairing to the RNA. And then, well, you go out and you can look around, etc. Okay. And then another example I have here is the same protein, a protein bound to a DNA molecule. So again, I will place it into the real environment without the need of any marker, just because the smartphone recognizes a flat surface, in this case the floor. And then you can move around and you can see interactions between the helix of the protein that reads the DNA. You can even point at the salt bridges that stabilize the interaction. Okay, and well, you can move around, same as in the other case. Okay. So everything I'm telling you here, you can find on my website or on the website of the server. And then going back to my list, I wanted to show you that one of the activities that we are developing is this one called the Virtual Modeling Kit. This tries to be a kind of alternative to the plastic models, but where you actually handle a molecule with this augmented reality marker. Okay, so you can come here and you paste any molecule that you want to try. I will show you some examples that are preset, but you can place really any molecule. Okay, not a huge protein because it will crash, but any small molecule will be okay. And then, so I wanted to show you here, for example, adamantane, which you know is these fused cycles, which is a bit hard maybe to understand in, where is it? It's maybe a bit hard to understand on paper. If you see it, you can tap here, adamantane. So these are the coordinates that you can get from any program. You can even build them. There are web tools where you can easily build any molecule, okay? And you can see it here, and by moving the cube, you can move it in 3 directions. So here you see that you have 1, 2, 3 rings, which are quite, they are much easier to draw or to see in 3D than if you do this on paper. And then here we have many options. For example, we can zoom in a bit if the molecule is too small, or you can zoom out if the molecule is big. Okay. Now we'll load another example to show you, just to show you another thing. So I will press F5 to refresh, continue, and then I will load. We have some crystals like salt. It should be somewhere. Okay, or this is sand, silicium oxide. I can start AR, okay, and you can see the arrangement, the crystalline arrangement. We can also change this visualization to see everything as spheres with this. Okay, there's another one which is table salt, so where sodium chloride, where you can also see the atom arrangement. Then we have this is also nice. F5 again. we have some small molecules, and one in particular I wanted to show you is small organic, maybe this one. This is a carbon with 4 different constituents, so it will be a chiral carbon. Okay, I will zoom in a bit to see it bigger. Here you have it. And then suppose you're teaching stereochemistry, you can easily click this to change the view. So you can see how the green is here, the red is down here, and when I click that, they swap, because I'm swapping the stereochemistry. Maybe you can also swap it here. Now you see it coming from right to left. Okay, I'm swapping multiple times. So this will give you the enantiomer somehow. Then another thing I want to show you is that we implemented dynamics, very simple dynamics that look like they are not very detailed molecular dynamics that you can use for actual simulations. They are more like they're trying to reproduce what the dynamics that you could have with a plastic model at the moment. Maybe in the future we will make this more detailed. So I will take the molecule. I have it. I'm looking at my list. Where is it? This one, 2-butanol. So you have all the carbon atoms, the hydrogen, the oxygen. I start this. You see it here. I will zoom a bit more. Okay. From time to time we have surveys. Please, if you use the server, fill these surveys and also tell your students to fill them. Okay. And what I wanted to show you here is that we can play with temperature. So when we load the molecule, the temperature is 0. So the molecule is frozen. There's no mechanics because there's no temperature, so nothing can move. But we can slowly begin to increase the temperature, and you will start to see that the molecule moves, okay? And then you can suddenly take the temperature to 0 and see what happens. Well, here it went back to the starting conformation, but I will give it some more, and then we'll place stop, okay? Here now you can see that the dihedral angle between the 4 atoms is roughly 0, so this corresponds to a kind of a thin conformation where the atoms are on the same side. Okay, and then you can continue, and maybe at some point probably you will go back to the anti-conformation somewhere here. If you do this with cyclohexane or with glucose, you will start to see all the changes between chair and both conformations. And this is trying to reproduce somehow the dynamics that you could have in a plastic tool. Then some other things that we have here, as for example, some carbon allotropes we have. One that may be nice is a carbon nanotube, so I will open it here. Here you can see it. You could also activate dynamics. You can activate dynamics on any example, not just on that one. I show you that one because it was interesting, okay? You can get inside the molecule here, look around. We have also diamond, graphite, etc. And well, then there is a video. I cannot show you all the examples, everything you can do, but I have a video here on my channel. This one, it's a bit long, but it shows you everything you can do with this kind of spirit of using this for your classes. So I will switch on my camera again to go back to the presentation. Wait, I need to stop this activity, and then here start the webcam again. Allow. I don't know why I have to say it twice. Start sharing. You should see me again soon. Hello. Okay, I think you see me now, and I will go back to my PowerPoint. So yeah, these are just some examples. You can see more in the videos or play yourself. So I will skip, but these are just photos of me. For example, here I tend to use these so that the phone can stand, and you see through the phone in this case, but you can also reverse the camera, and then you use it like in the computer, okay? And then the secondary structures, this example I show you, here are some molecules with balls or sticks. This is a YouTube video where I explain many of these things. Then these are the contents that we cover. I kind of told you already, but here are the details. I will leave this presentation on my website so that you can download it if you want. Then we have atomic orbitals, molecular orbitals. This is a remake of a paper that a friend from Cuba, he did a couple of years ago, but it was with a program that you have to download and start. We repurpose it to the web so that you can use it right away within the website. Then some cases they have interactions. For example, here is DNA and protein that you can move independently. When they are close enough, the computer tells you, look, I can make this interaction, and then you can dock the two and you can release one, and you will handle the complex to point at things. Here I'm showing you more on other molecules in the virtual modeling kit. For example, here this is cholesterol, and we are zooming on this carbon because we are paying attention to the chirality of this carbon. And then here you have some more cases. This is a sodium chloride I told you about. These are proteins. This is an alpha helix from a protein. This is a heme center in a protein. Then these are more pictures of the one I cannot show you on the computer because it runs on the phone only, but I show you the video. One of the cases we have is this virus. This is coming from an experimental tomography where the virus got caught when it was inserting the needle through the membranes of a Salmonella bacterium. And you can walk around, see the needle. You can even go inside the capsid. Then you look down and you see this. You see the needle from inside. So it's quite nice to explore. This is a zoom of the same thing. And then an important point with all this is, okay, it looks nice, but we have to follow user reception. So far, when we had the preliminary activities, this was still part of a hobby, there was an outreach event at EPFL, and also we visited some schools. We were trying there with adults and also with students. We did lots of tests around the world. I'm using it in some YouTube videos where I teach some things very slowly because I don't have time. But we know some people that are using it for online teaching, especially with the pandemic. It turned out to be a very interesting tool. This is very easy to share. You just tell somebody to go to the website and they can run. Well, they have to print the markers, but it takes a couple of minutes only. We are following website usage through analytics, and here I'm showing you, for example, the usage that we see since we released the website. You see people from all over the world. Of course, there's a lot of people from Argentina and Latin America because you have my videos in Spanish. There are some people that tried it from Brazil. That's why I was interested in coming to the conference, to let you know that you can use it to your students and communicate about the site. There's a lot of usage in America because I know some professors there that started to spread it. There's a lot in Europe also. Some people from Australia contacted me, but we want people to use it. It's for free and on the web, so it will be nice. It was recently highlighted in this Mesos in Molecular Biology thing, so I'm happy to see that. In the future, we want to use it also for research. At the moment, it's only for teaching. That the activities allow only that. Then this is an example in one of the outreach events where we had some students that were teaching the public about. There were different activities in augmented reality that they were trying. One of them, for example, was the virus, and you see people playing. We saw that it's very engaging, especially kids and young adults. They show very good coordination with the things. Maybe older people got a bit complicated, but okay, they are not coming from the generation that plays video games like we are and the younger people are. But the usage was quite good, quite easy. And some of the students, it was very interested, were even interested in the programming, because when you have this kind of web apps, you can do Control-U in any browser and you will see the code. It's a code that you can read and see. So they knew that, and they wanted to see how the code works. So they were not interested in the chemistry, in the biology, but they were attracted to understand the programming. And then, as I told you, some teachers are using this during the pandemic for their students to do things. And well, one of these teachers, she contacted me, so we started to do a kind of collaboration, and she tried the website on some students, on like 30-something students, and we had a small survey that they filled. You see one of the students here. Of course, they have to cover the face. Then another student here playing. She made sure that they actually tried the website by asking them to show a picture of the markers to see that they were really trying it. Before they say, no, I couldn't make it work. And the results of this so far are okay. We see a lot of engagement, seems to work out of the box quite well. So more than 75, almost 80% of the students could make it work without any help, because this is tele homework. They are not going to the school, okay? There's a quarter maybe that couldn't use it well, but the teacher, she knows that some people maybe have a very poor internet connection, some of the students, etc. Problems that you have in Latin America, okay? Students seem to have perceived utility. This is coming from the survey. We are trying to do some experiments with other teachers to try to explore this further. If the perception is real, that they really get something useful, or it's only that they think it's useful, but it's actually just playing. And as I told you, it fosters some interest also in this. like we have here, that some people got interested in the programming aspects. And then what do we want to do next? So the next we want to do is to have this cube, but two actually, so that you can load any molecule on the cubes and then make them interact, or maybe you can load, say, a butane molecule and grab it with the two markers to force a rotation. So instead of depending on the dynamics, which is a bit random, so that you can force this as if you were playing with a plastic tool. And then, well, for further things, we are waiting to hear from you and all the teachers around the world who are using this. The activities are tailored more to high school and maybe the first years of the university, especially general chemistry and organic chemistry, some chemical biological chemistry as well. And it's important that if you use it, you tell us if you find bugs, if there are conceptual problems. For example, the alpha helix I show you here is okay, but I realized yesterday that on the phone, depending on which camera you use, the alpha helix comes the other way around, which is conceptually wrong. It should be right-handed, it was left-handed, but okay, you can correct it as if you know about this. Then you can also ask us to write to us to propose new activities, or even in the activities that already exist, try to propose new molecules. Now our focus is in developing more the biological, the cases of biological molecules, but perhaps some other activities are interested as well. So with this, I will stop here. I recommend you to go to the videos to see more, and you can also read the preprint that is somewhere here. I will leave this presentation in my website. And if you have any requests, you can ask us. And well, with this, I thank all these institutes and people that funded the work that led me to slowly to do this. So with that, thank you. Maybe I can leave you with this in case you want to take your phone and try it while we speak. If you have any questions, I can take them.
Thank you. If someone has any question, please write in the chat, and we, open your mic, and you can go ahead and make questions.
You can ask me in Portuguese. I will also understand. Okay. I think.
Marcelo. We have a question.
Mm-hmm.
Any question? Open your mic and make a question.
Carolina says she has a question.
Carolina.
I leave this in case you want to take the phone and try.
Yeah. Carolina, your mic. Now she's okay. Your mic is disconnected.
No. Hello, everybody.
Hello.
Luciano. Congratulations for your work. I'm a chemistry teacher. I teach general chemistry and organic chemistry, and I'm certain that it will be amazing using your material. Thank you for presenting it for us. And my question is, where can I find the markers? I was checking your website.
We know we have to put them more explicit in the website. We will do this in the front page, but for the moment in the preprint, you should see it.
Okay.
As a supporting information. I can go quickly there, maybe from the website. Website, and then about the paper should be somewhere here. Yes, if you go to this preprint, in the supporting information view, one of the first pages are the markers. Actually, you have marker 1 at 3 different sizes, so you print the one that you like better. You can also resize it. Marker 2 for the activities that use 2 markers. You have this thing in the middle to fold it and glue it. And then if you want the cube marker, which is what most people use actually for the molecular virtual modeling kit, you have it also here. Okay, and this is all open. You can just go and take it and print.
Perfect, thank you. And another question is, you pretend to do some material about coordination chemistry?
I didn't do much because it's been like 15 years that I studied that. I'm really not using it. enough to build material. But if you have ideas, they are super welcome. Huh?
Okay. Thank you again.
Write to me by email, and we arrange what kind of material we can prepare.
Thank you. Thank you, and congratulations again. Bye.
You're welcome. Thank you.
Okay, more questions? It's not showing. Let me make one specific question. When you make the interactions, you show the two molecules and then they interact. Is this zero temperature interaction?
Yes, it's not doing any dynamics on the molecules. They're just.
And do you have any constraints regarding size of your system, the system size? For instance, even if zero temperature and I have a graphene sheet and I want to understand how a molecule approaches the graphene sheet, do you have any constraint size of that? So what's the molecule size you can handle with this?
If you want to do it with a molecular modeling kit, so we are representing each atom individually and we are propagating the physics, etc. So the limit, I don't know exactly, but maybe 100 atoms, something like that.
Okay.
It depends also if you do it on the phone or on the computer, the power of the computer, but say around 100 atoms. What I have to say anyway is that what the physics that we have there are very simple. So there are just clashes between atoms. We want to start to have charges and that, but it's not like what you can do with a real molecular simulation.
Ronald Dickman is asking, could you use color change to represent repulsion or attraction between molecules?
Yeah, actually, the next step, when we will have this that I was showing, when we want to do this, we actually want to incorporate into the force field that we use, we want to incorporate some attraction and repulsion, okay? And then we also want, so you will feel it somehow. If you approach two molecules that have the same charge, suppose that the charge is on the tips, then they will start to, as you try to put them together, they will start to move away, okay? We could also, if it's interesting for some reason, we could also show the color, the charge by changing colors. But in principle, if we see the repulsion, it's even better. So yeah, somehow, yeah, it's relatively easy to do that, what Ron asks. Welcome, Ron.
So if there is no further question, let's thanks in the electronic way. And
yeah, electronic applause.